Hi everyone. Today we're going to study proof using well-ordering property. The well-ordering property states that every non-empty set of non-negative integers has a least element. Example 1. Use the well-ordering property to prove division algorithm. If a is an integer and d is a positive integer, then there are unique integers q and r with r is between 0 and d, and a equals dq plus r. Remember, a here is the number, d is the divisor, q is the quotient, and r is the remainder. Also, the range of values of r is 0 and less than d. We let capital S be the set of non-negative integers of the form a minus dq, where q is an integer. This set S is non-empty because negative dq can be made as large as desired, meaning taking q to be a negative integer with large absolute value. By the well-ordering property, capital S has a least element, and that is the r equals a minus d times q sub 0. We assign now a specific value for this q, and that is the q sub 0 for the least element, and that is r. Take note that the integer r is non-negative. Also, r is less than or equal to d. Now we have this proof by contradiction. What if r is less than or equal to d is false? Then there would be a smaller non-negative element in S. Namely, now this is a minus d times this quantity q sub 0 plus 1. To see this, suppose that r is greater than or equal to d. Because we assigned the least element a while ago, that a equals d times q sub 0 plus r. Because of this contradiction principle, it follows that a minus d times the quantity q sub 0 plus 1. Then let us simplify this negative d to be multiplied to the terms inside the grouping symbol. So we have now this a minus d times q sub 0 minus d. Now look at this a minus d times q sub 0. A while ago, we set this as this value r. Let us substitute r in here. So we have this r, then this minus d. This value here must be greater or equal to 0. Then we can move this negative d on the right side of the inequality. So we have r is greater than or equal to d. Remember, r is the remainder and d is the divisor. With this greater than or equal to symbol, this is a contradiction to the division algorithm. Hence, S has a least element, and that is R equals A minus D times Q sub 0. Example 2. By well-ordering property, show that there are no positive integers strictly between 0 and 1. Let capital S be the set of non-negative integers such that x is between 0 and 1. Suppose capital S is non-empty. By the well-ordering property, there exists smallest integer n, such that n is less than 1. We take a value between 0 and 1 and square it, and this will be true, that n squared is less than 1. If we put together this n and n squared between 0 and 1, we will have this inequality. 0 is less than n squared is less than n is less than 1. Look at this, n squared is less than n. There are many values between 0 and 1 that will satisfy this inequality. Therefore, this contradicts the fact that n is the least element in S. Therefore, S is empty. Hence, there are no positive integers strictly between 0 and 1.